The sum of the squares of the first n natural numbers can be written like this: sigma r equals 1 to n of r squared. And here it is. We put 1 in for r, we get 1 squared. Then we put 2 in for r, we get 2 squared. Then 3 in for r, we get 3 squared. And so on up to r equals n. So the last term is going to be n squared. And it turns out that this sum can be written as n times n plus 1 times 2n plus 1 all over 6. For example, suppose n is equal to 2 and we want to sum our series from r equals 1 to 2. Well, that's just going to be 1 squared plus 2 squared. 1 squared plus 2 squared is 5. Now, let's just see what happens when we plug 2 into this expression. Well, we get 2 times 2 plus 1 times 2 times 2 plus 1. 2 times 2 is 4, so we get 4 plus 1. So we get 2 times 3 times 5, all divided by 6. So we end up getting 5. So it does check out for n equals 2. And you'll see yourself, if you pick any value of n you like, it does actually check out. To prove this summation, I'm going to make use of this identity. Now, what is an identity? An identity is an equation that's true for all values of the variable. So this thing here must be true for all values of r. An equation might only be true for some values of r. So basically, if we expand out the left-hand side and simplify, it should all break down to 6r squared plus 2. So I'm just going to show you that this identity is indeed true before I use it. First of all, I'm going to show you what the cube of a binomial is. So here we have a binomial expression, two terms. We cube the first term, a cubed, plus 3 times the first term squared by the second, plus 3 times the first by the second squared, plus the second term cubed. Now this thing comes from the binomial theorem, but it's just useful to remember it in words, like I said. So if we look at the left hand side here, we have r plus 1 cubed, so we've the first term cubed is r cubed, plus 3 times the first squared by the second term, 3r squared by 1, plus 3 times the first term, which is r times the second term squared, 1 squared, plus the second term cubed, 1 cubed is 1. Then we have a minus sign. We cube the first term, plus 3 times the first squared by the second, that's going to give minus 3r squared, plus 3 times the first term by the second term squared, that's going to give plus 3r, plus the second term cubed, minus 1 cubed is minus 1. So this thing should all break down to 6r squared plus 2. You can see that the r cubes cancel out. We have plus 3r squared minus 3r squared. That's going to give us 6r squared. We have plus 3r minus 3r. 3r's will cancel out. And we have plus 1 minus 1. That's plus 1 is plus 2. So this identity is indeed true. So it doesn't matter what value we put in for r, this thing will be true. Now you can see that r squared is part of this identity. So what we do is we sum the left hand side from r equals 1 to n. But of course if we sum the left hand side, that is all of this here, from r equals 1 to n, we have to sum the right hand side from r equals 1 to n. And you see that's how we can bring in sigma of r squared. Now first of all I want to look at the right hand side of this identity. The right hand side is sigma r equals 1 to n of 6r squared plus 2. We can actually write this thing as 6 times sigma of r squared, r equals 1 to n, plus sigma of 2 from r equals 1 to n. So that's how we can get at sigma of r squared, which is what we're looking for. Now I'd better explain why we can do what I just did, why we can break this thing into two parts and pull out the 6. So one way to show you that would be to actually do the sums on both sides. So if we start with 1, we get 6 times 1 squared plus 2. That's for r equals 1. Then we put in r equals 2. So the next term is going to be 6 times 2 squared plus 2. And we keep going until we get to the last term, which is n. So we get 6 times n squared plus 2. But you see, we can write this in any order we like because we're just adding things. So we could actually write this thing as 6 times 1 squared plus 2 squared plus dot 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 as far as n squared plus all the 2's. We can add up all the 2's. But how many 2's do we have? Well, we have n of these terms. N terms in total, going from r equals 1 to n. So we actually have n 2's added together. N 2's can be written 2n. But you see, this thing here is exactly what we have on the right hand side. You know, this is just 6 times this sum here. But this thing here is the sum of the squares of the first n natural numbers, which is what we're looking for actually. And as for the 2n, well, the 2n is just the sum of 2 from r equals 1 to n. Okay, the meaning of this thing here is that we start with 1 and we write down whatever we have here, which is 2. There's no r in it, there's no dependence on r, so we just write it down. It's just a constant. So when r is 1, our expression is 2. When r is 2, it's also 2. When r is 3, it's 2 as well. So this is a constant function. It doesn't matter what value of r we put in, we just get the constant 2. And we get it n times, because we go up as far as n. So we have n 2's, which is of course 2n. So that shows that we can take sigma in through expressions like this. We can distribute sigma through pluses and minuses, and we can pull out constant factors. 6 is multiplied by r squared, so we can pull that outside the sigma symbol. And when we're summing a constant term, like summing 2, we just multiply that constant by the number of terms that we have. And we have n terms because we're going from 1 to n. So that's the right hand side. Now let's look at the left hand side of our identity. Well, we start with r equals 1. We plug 1 in here, so we get 1 plus 1 is 2. So we get 2 cubed. I'll leave it like this. Minus, then we plug 1 in. 1 minus 1 is 0. 2 cubed minus 0 cubed. Actually, I'll leave out the 0 cubed. That's just 0. So this is the first term corresponding to r equals 1. Then the second term corresponds to r equals 2. So we plug 2 in here. 2 plus 1 is 3. 3 cubed. I'll leave it like this because you'll see the pattern soon. Plugging 2 in here, we get 2 minus 1 is 1 cubed. So this is the second term. You can bracket it if you like. The third term is got by plugging 3 in. 3 plus 1 is 4. So we get 4 cubed minus 3 minus 1 is 2. 2 cubed. Plus, let's see now, we want the fourth term. 4 plus 1 is 5. 5 cubed minus 4 minus 1, which is 3. 3 cubed. Now I've written down the first 4 terms. What I'm going to do now is skip on, dot dot dot, and I've moved on to the next line to get some space, and I'm going to write down the 3 last terms. So the third last term is going to be Tn minus 2. To get Tn minus 2, we plug n minus 2 in for r, so we have n minus 2 plus 1 is n minus 1. So we get n minus 1 cubed. Then we have a minus sign, bracket, n minus 2 goes in for r, n minus 2 minus 1 is n minus 3. So all of this here is Tn minus 2. And to get Tn minus 1, we plug n minus 1 in for r. So we have n minus 1 plus 1 is n. We get n cubed there. Then we have a minus sign. Plugging n minus 1 in here gives n minus 1 minus 1, which is n minus 2 cubed. So this here is the second last term, Tn minus 1. And finally we get to the last term, Tn, which is just got by plugging n into this, so we get n plus 1 cubed minus n minus 1 cubed. Now I need to write out several terms at the end in order that you can see what's going on, because this series is going to telescope down to a few terms. Just like you saw in the previous video, which is called Telescoping Series. And you'll see that most of it cancels out and we're just left with a few terms. So we see that the 2 cubed minus 2 cubed gives us 0. Of course, we can remove all the brackets and combine them any way we like. The 3 cubed cancels with minus 3 cubed. So the first part of each term cancels with the second part of the term that is 2 terms ahead. So the first part of T2 cancels with the second part of T4. Similarly, the first part of T3 will cancel with the second part of T5, which I haven't written down. The second part of T5 will be minus 4 cubed. The first part of T4 will cancel with the second part of T6, which I haven't written down. Of course, I could reverse what I said. I could say that the second part of each term, like the second part of T4, cancels with the first part of the term that's 2 terms previous. So the second part of T4 cancels with the first part of T2. So in particular, at the very end, the second part of Tn cancels with the first part of Tn minus 2. The second part of Tn minus 1 will cancel with the first part of Tn minus 3, which I haven't written down. The second part of Tn minus 2 will cancel with the first part of Tn minus 4. However, the first part of Tn minus 1 will cancel with the second part of Tn plus 1, but there is no Tn plus 1. Okay, so this n cubed doesn't cancel with anything. If it was to cancel, it would cancel with the term that's 2 terms ahead of it. But there is no term 2 terms ahead of Tn minus 1. So this part doesn't cancel. Similarly for n plus 1 cubed, that doesn't cancel either, because it's the first part of a term, so it should cancel with something that's 2 terms ahead of it. And there's nothing ahead of it. So what we're left with is minus 1 cubed, which is minus 1, plus n cubed, plus n plus 1 cubed. Everything else cancels to 0. So now we've got the right hand side in terms of n. And we want to equate this with the left hand side so we can find what we're looking for, which is sigma of r squared. So here's the right hand side written down. Remember, sigma of a constant is just that constant times n when we're summing from 1 to n. So this term here is just 2n. So to get sigma r squared, we just bring the 2n over and it becomes minus 2n in here, and we divide all of the right hand side by 6. Now we've got to show that this expression here is equal to n into n plus 1 into 2n plus 1 over 6. To show that these are equal, what I will do is I'll expand out the numerator of this. The denominators are equal, so we can forget about the denominators. We only have to compare the numerators. So expanding out this numerator, we get minus 1 minus 2n plus n cubed plus cubing this binomial, we get n cubed plus 3n squared times 1 plus 3n by 1 squared plus 1 cubed. Tidying this up, we get 2n cubed plus 3n squared, 3n minus 2n is 1n, and these ones cancel out. Now I'll multiply out the numerator of this expression. So we have n into multiplying n plus 1 by 2n plus 1 gives 2n squared plus n plus 2n is plus 3n plus 1. And that gives us 2n cubed plus 3n squared plus n. So that shows that what we got is indeed equal to what we were setting out to prove. Now I could also do a proof by induction, but I won't put this in the series playlist. I'll put it into the proof by induction playlist at some stage.